My name is Luke Seibold, and this is PhyziX, where we're going to be learning about momentum. I actually play quite a bit of rugby, and in rugby, we often talk about carrying momentum into contact. But what exactly is momentum? Well, momentum, which is often given by the letter P, is actually a product of mass times velocity. Now, often rugby players are very big, so they have quite a bit of mass, which will be what gives them the momentum to tackle people and take them down. But me, on the other hand, I'm not so big, so I have to make up for this with my velocity. So if I'm able to increase my velocity enough, then I can generate the same amount of momentum as someone who might be much bigger than me. Now, the change in momentum is what we call impulse, and change we're going to show with the Greek symbol delta. That's the Greek symbol delta. So delta P, change in momentum, this is what's known as impulse, and is equal to either the change in mass or the change in velocity. Now, in dealing with impulse, what we're usually dealing with are collisions, because things will only change velocity when they experience another force that is acted upon it, and so therefore that will usually come from a collision. And now these collisions are governed by the law of conservation of momentum. Now, this law states that the total linear momentum of a system of interacting particles remains constant provided there is no resultant external force. So basically what this means is that the total momentum between two things that are colliding with one another will remain the same even after they've collided with one another. So let's picture we got two rugby players running into each other. One's a little smaller than the other. He's 50 kilograms, and he's running at 10 meters per second, so times 10 meters per second. So that means that his momentum would be 500 kilograms times meters per second. Now, the guy who's trying to tackle him is much bigger. Got a big dude trying to tackle him, and he is 100 kilograms. So let's say they collide into one another and they stick together. So the big guy grabs onto the little guy and they stick together as they are colliding. So that means that their new total mass will be 150 kilograms. And if momentum is said to be conserved, then the momentum, which is 500 kilograms times meters per second squared, just meters per second, will be equal to their total mass times their velocity. And so their velocity will be equal to 500 kilograms times meters per second divided by their total 150 kilograms. So as we can see, the units cancel out there. 2 kilograms cancel out. And we are left with a velocity of 3.33 meters per second. So even though this huge defender is much bigger than this guy, because he doesn't have any velocity, and the smaller guy is coming in with quite a bit of velocity at 10 meters per second, then even the big defender isn't going to be able to stop him, and he's going to continue to be moving. They're going to continue to be moving at 3.33 meters per second. Now, this is what is said to be an inelastic collision. Now, we also have what are known as elastic collisions. So let's take a look at what those are. So to illustrate these collisions, we're going to imagine we have two identical boxes that are colliding into one another. So they will both have a mass of m, and m. Now, if this box comes at this one with a velocity of v, It will be an elastic collision if the box then just stops right there and all the velocity is transferred into this block. And so its velocity will then also be v, because this velocity reduced to 0 once it came to rest over here. All the velocity is transferred into this one, and that is what is known as an elastic collision. And we've already looked at inelastic collisions, but let's look at them again with this more simplified version. So let's imagine we're dealing with the same two blocks of equal mass, m. Now, this block comes at this one with a velocity of v, but because of the material that they're made of, they actually end up sticking together and moving together. So that means that their total mass will then become 2m. So we have 2 m's moving together. And so P, which once equaled mv, the mass of the first block times its velocity, now it has twice the mass because there are two different blocks. But momentum has to be conserved. So in order for it to be conserved, we divide its velocity by 2. Because these will cancel out, 2 divided by 2 just equals 1, then momentum will remain the same. However, the mass will have increased because now we have 2m, while the velocity will have decreased. So this is not actually accurate because it is just as long as it was before. Now it will only have half the velocity as we showed here. Now its velocity is half that it once was, and the two blocks will remain stuck together. Now if we look at this equation, we can see that it's actually pretty similar to our equation for force, which is F force is equal to mass times acceleration, except instead of acceleration we have velocity. So let's see if we can somehow relate force and momentum or impulse. So if acceleration is velocity over time, then we get that F force is equal to mass times change in velocity over change in time. And that's because acceleration is equal to change in velocity over change in time. Now, this will give us the equation that F is equal to m delta v over delta t. Now, where have we seen this before? That's right up here. When we have a change in velocity or a change in mass, then we're going to have a change in momentum. So this is actually impulse. So this gives us the equation that force is equal to impulse over time, change in time. And that's because impulse is equal to mass times change in velocity. We can therefore say that force is actually the rate of change of momentum over time. So what exactly does this mean? Well, in order to understand it, let's go back to our little example with our two rugby players. And for simplicity's sake, let's imagine that they're the same size this time. So this guy's getting ready to tackle this other guy. And let's say they're both 50 kilograms, both coming in with at 10 meters per second. So they both have momentum of 500 kilograms times meters per second. This guy's also coming in with 500 kilograms times meters per second. Now, the tackler is actually going to be able to stop him in 2 seconds, let's say. 2 seconds. And so, therefore, if force is equal to change in momentum or impulse over change in time, and if the guy with the ball is brought to a stop, then his change in momentum will go from 500 kilograms times meters per second to 0, because his velocity drops to 0 when he's stopped. So the whole thing will be 0. So the change in momentum or impulse will be 500 kilograms times meters per second, all over the 2 seconds that it took the tackler to do it. And so this will give us 250. And if we look at what the units are, well, then it comes out to be kilograms times meters per second squared, because when you have seconds to the -1 minus seconds to the 1, because it's being divided by seconds, then you get seconds to the -2. And where have we seen that before? Oh, that's right, it's newtons. So that shows us that this is a unit of force. So the amount of force that the tackler is applying to him is actually 250 newtons. Now, when training for rugby, we don't want to get hurt, and so often we'll use tackling pads in order to practice tackling. Now, why does this make the contact hurt any less? Well, I'm going to show you. So let's imagine we have that same dude coming in to tackle this pad, and he's got, again, 500 kilograms times meters per second. And now he's crashing in to this big soft blue pad. The soft blue pad is going to take longer to bring him to a stop because he's squishing into the blue pad. It's going to take him all of 5 seconds to go from 500 kilograms times meters per second squared to 0 meters per second squared, and so 0 kilograms times meters per second. I keep saying meters per second squared, I mean to say just meters per second. And so if this is the case, then force, which is equal to change in momentum over change in time, will be equal to the 500 kilograms times meters per second over the change in time, which is 5 seconds, giving us 100 kilograms times meters per second squared, or 100 newtons. And now this is significantly less force than the 250 newtons that came from smashing in to a much harder rugby player. If the material we have is softer, it'll take the tackler longer to come to a stop, and therefore there will be less force on him. So I actually have momentum and physics to thank for the fact that I haven't been hurt too many times when playing rugby.